Our chapter 2 on fish ears is going to be about the perceptions of fish. So we talked about the mechanical systems of how fish hear, and now we're going to see what they do with this information. All animals are adapted to their environment, and so when you have a situation where you are a schooling animal, you need to figure out how to come up in close proximity with your conspecifics. If you are a sedentary and solitary animal, you need to have sensory systems that will allow you to sense your predators as they approach you, and also as your prey, because there is not the same kind of adaptations in a schooling situation with a sedentary solitary fish. If you are a flatfish that relies on disguise at the bottom of, laying on the bottom of the ocean, you don't necessarily need to have, for example, a swim bladder, because you're going to always be on a flat surface. So all the different fish have adapted to these particular environments in particular ways, and well, I guess the kind of the overarching story here is all animals have adapted to their auditory environment with organs and perceptual systems that help them establish their most optimistic or opportunistic relationship with the surrounding. So if we take the lateral line, it has cilia along the side of it that sense particle motion. So as the fish moves, or as information changes around the fish relative to proximity of other moving bodies, it translates as particle motion onto those. So this is one of the ways that fish, actually schooling fish, can keep in close proximity with each other and sense the movement of their neighbors. And so they don't necessarily need to see when a fish school is being attacked by a large predator from behind. That energy of that, the particle motion energy of that, impinges on the whole school of the fish. And the school of fish moves as a single body to avoid that predation. And they do that by synchronizing on these lateral lines. So if you suspend fish in a really loud environment, the louder it gets, the more that these schooling fish will drift apart. At some point in time, they'll disorient. They're no longer schooling fish. They're individual bodies, bags of protein. So that lateral line is adapted to sense the motion of adjacent bodies. There's an interesting thing that happens in terms of how sound or acoustical energy is conferred in the water relative to particle motion, which is sensed by the lateral line, and also sensed by the otolith and the sensory epithelium in the skull of the fish, and the swim bladder, which confers pressure gradient energy. In the near field, that is, if a sound is generated close to the fish, there is a lag, a phase lag or time lag between the particle motion and the pressure gradient. So the pressure actually lags the particle motion. What that does is allows the fish to tell how close something is. So in the far field, there is not this pressure lag. The particle and pressure gradient really comes in at the same time. So the proximity of whatever noise is in the environment is perceived as a time gradient or time distinction. So that would be a reason why an animal in the water would maybe be alerted by a very quiet noise that's close to it, even though it's surrounded by lots of loud noise. So the example I like to use is you take a trout swimming in a stream. The stream is very turbulent. There's lots of water and splashing and what have you. It's a very noisy environment. But a little caddisfly lands on top of that water, and that trout knows exactly what's going on. So very quiet noise, it might be 50 or 60 dB difference in terms of the noise of the caddisfly landing and the noise environment. So it's an interesting way that animals who live in turbulent or noisy environments can actually still perceive proximity of sound to them. It's a discrimination that happens. Another part of the hearing system of the fish is the swim bladder. And there are a number of different types of adaptations to this. But one that we're going to talk about here is one that's fairly tightly coupled through the vibarian ossicles. There's 4 bones there. We don't know why there's 4. Again, I always come up to this idea that nature is elegant but not extravagant. So there's 4 bones for a reason. We don't know why. But seeing as terrestrial animals only have 3 bones, there's something in that 4th bone that is conferring information to these animals. So while when you look at the fish audiogram, these tests that allow us to determine the sensory thresholds of the animal to certain frequencies, it looks fairly lousy in most fish. But we may not be getting the whole story, because oftentimes audiograms are only done in pressure field, near field pressure gradient energy, and the particle motion is not part of it. It's very difficult to test particle motion because of the nature of the environment. So there may be more information on fish hearing which we are not getting. I'm very suspicious of that.